Hey there, folks. I hope you've all had a great weekend. Let's apply the concept of work that we've been covering to a familiar type of block and pulley problem that we covered a couple times from the last chapter. The first thing we'll need to do here is draw some free body diagrams. So let's get started. On the left, block A's weight will point in the downwards direction, which I've set to plus y in this coordinate system. And the normal force from the table will point in the opposite with equal length, since this block only slides across the table to the right. The tension from the string that's attached to block A will pull towards plus x, and since we don't have to worry about friction yet, we can move on to the other block. The weight of that one will also point downwards, and in the opposite direction lies the tension. Since we know that block B will accelerate downward once we release the system from rest, don't forget to draw the tension vector smaller than the weight vector. Speaking of accelerations, we can include vectors for those as well. That's it for this step. On to the sum of forces. There's only tension acting in the x direction for block A, which makes things fairly easy here. Let's divide both sides of this expression by the mass of block A, which will give us an explicit form of the acceleration that we can use a little bit later. The y direction is also pretty simple, since the weight and the normal force balance each other out. We can equate these two, but the result won't be handy until later. Moving on to block B, there's nothing occurring in the x direction at all, since this block only moves vertically. In the y direction, however, we have the following. There's nothing we can simplify here, so let's see if we can use this in conjunction with our acceleration expression from earlier to get the tension. We'll need to figure out how much work the tension does in order to solve part A in its entirety. If we start with that equation from before at the top, then plug in our acceleration expression, we can multiply both sides by the mass of block A here to get rid of this denominator. Go ahead and distribute that mass in on the left-hand side, and at this point we can move the term with tension in it over to the other side, which places all the tension terms together on the right-hand side, and we can factor it out. Divide both sides by the sum of masses on the right, and now we've got it. When you plug the numbers into your calculator, you should get exactly 7.5 newtons for the value of that force. With T known, we can now calculate the net work done on both blocks and get part A taken care of. Let's start with block A. The work done by the weight is 0, since the weight doesn't displace that block in the vertical direction at all. The same goes for the normal force. In fact, the only force doing work on this block is the tension of the string. When we multiply the force of the tension by 75 centimeters, which we'll have to convert to meters, by the way, just a heads up, we'll get the following result in Newton meters, which is the proper units for work. Round it to 3 significant figures, and here is the net work done on this block. For block B, the weight does do work, since that block is displaced in the same direction as that force, and the same will apply for the tension. We'll have to sum these values together in order to get the net work, and again, answering to 3 significant figures, we get the following. And those are the answers to part A. For part B, we'll have to go back to the drawing board and incorporate friction into our free body diagram. The only place that it acts here is to the left on block A. All the other forces stay the same, but do take notice that the accelerations will have a new value. The sum of forces will certainly change in the x direction now for block A, and we can exchange out the kinetic friction term for its definition. At this point, you might be wondering, don't we have to include static friction somewhere since it was provided for us earlier? Well, the answer is no, because the problem is trying to trick us with that quantity. We won't be using that at all. Static friction cannot do work since it only pops up when an object is stationary. And if an object is stationary, it's not being displaced at all. In the last part, we saw how the normal force was equal to block A's weight. It's the same situation here, so go ahead and grab that result, plug it in for n, and save yourself on some writing. Let's make use of this result in just a moment. Before we do, just a heads up here, we can ignore doing the sum of forces for block B again, since everything remains the same except for that new acceleration. With that said, let's go ahead and take a closer look at this underlined equation here. We can do the same process like we did before, where we isolate the acceleration variable. Pretty simple here. Just divide both sides by block A's mass, and that's it. We'll take this result and plug it into the y direction equation from the sum of forces on block B, since that didn't really change except for the new acceleration. When we put that in, we can multiply both sides by the mass of block A again to get rid of this denominator. And next, we can distribute the masses on both sides into the parentheses, like this. Let's exchange this negative tension term on the left with this other negative term on the right, which will bring everything containing tension onto the same side. Go ahead and factor that tension out, then divide both sides by the sum of masses. The result looks a little messy, but we know all of the values for everything here on the left-hand side. When we plug it in carefully into the calculator, we get the following value for our new tension. Let's go ahead and finish this part up now. The work done by the weight of block A and the normal force are still 0, so let's go ahead and get those out of the way and move on to the good stuff. Here's our work done by the tension as well as friction. Add those two values together and round to 3 significant figures, and now block A is all set. If we take the same work done by block B's weight from before and sum that with the work done by the new value of the tension, we'll get this quantity here. And now we have the net work done by both blocks for part B, or net work done on both blocks for part B, excuse me. Let's go ahead and bring everything together on the solution card. Here it's pretty plain to see that once we start involving kinetic friction for the second part, the total work done on our objects decreases by a rather noticeable amount. So we'll see that happen again in future problems as well. Thanks for watching, everybody. Have a great day.